Welcome to Module 1. In this module, I have a theory, or it's just a theory. Have you ever heard that before? Oftentimes when people talk about science, they hear that word thrown around a lot, theory, or as we covered in the last video, hypothesis. But those two words have very different meanings, but they're oftentimes used interchangeably, if not confused for one another. Or laws. You hear things about like the law of gravity or the law of evolution, um, or facts such as the sky is blue. Well, let's talk about these really quickly, how they're different, and why it's actually important to know the difference in science. So, first, let's talk about a hypothesis. What is the difference between a hypothesis and other things? So, theories and hypotheses actually are in the same category. They represent explanations as to why something occurs. A theory or a hypothesis is an explanation of why something occurs. So, the theory of evolution, for example, or germ theory. It's germs that make us sick. Those are theories. That being said, what is the difference between a theory and a hypothesis? Well, the big difference between them is one has been tested and has passed the test, while the other hasn't. So a hypothesis is an untested, unproven explanation. It's only based on what you know. Oftentimes, the two-word phrase that's thrown around is, it is an educated guess. A hypothesis is an educated guess. What that means is that it's based on information it's based on what we already know. So it is created prior to an experiment. And an experiment is designed to test it. Now, on the other hand, let's say we take our experiment, we test it, we ring it through the whole thing, and on the other end, the hypothesis checks out. The hypothesis checks out. If that happens, the hypothesis gets a little upgrade. It is then known as a theory. A theory is something, it's an explanation that has been tested and proven and accepted as true. So the big difference between hypothesis and theory, a hypothesis is untested, it's based on only what you know. And a theory actually has backing to it. It actually has been tested, it has passed its test, it has proven itself, and it is accepted as true. Basically, how a hypothesis becomes a theory is it gets tested and it gets proven. Now that sounds a little weird, don't you think? Have you ever heard of the phrase, I have a theory? Or maybe somebody's told you, it's just a theory. Theories get a really bad rap. And so I'm going to channel my inner Inigo Montoya. If you've never seen Princess Bride, please go see it. Or please see it. And people misuse this word so terribly. The colloquial definition of theory is it's a guess. So, for example, let's say I had a theory that more students sign up for online classes than for on-campus classes because they just want to be online. And I go, well, that's my theory. But if I have no data to support that, or if I have not tested that, it's actually not a theory. Instead, what I have actually just mentioned is a hypothesis. Now, how would I test the hypothesis? Offer some online classes and see how they enroll compared to offering some on-campus classes and see how they enroll. If after a few terms of doing that and always seeing the online classes fill easily while the on-campus classes don't, guess what? I now have a theory. So theories actually have a lot of backing to them. So when somebody says it's just a theory, they don't know what they're talking about. No, it's a theory. That means that it has evidence backing it up. It has passed the test. Whereas a hypothesis hasn't done that yet. It still needs to prove itself, or we still need to prove it. So hypotheses need to be proven, theories don't. Now, how do those differ from laws and facts? Well, hypotheses and theories are explanations of something that happens. So, for example, of why something happens. So let's say I'm holding a pen, I let it go and it falls. Laws and facts tell me that if I let go of the pen, it's going to fall. I mean, here on campus at De Anza College, on planet Earth, if I let go of this pen, 100 times out of 100, it's going to fall. But why does it fall? Well, it falls because of gravitational attraction. That is a theory. And that theory came to be after many, many, many observations of taking two objects of different masses and watching the smaller object attract to the larger object. That is how that theory developed. Before that, when the apple first hit Isaac Newton's head, he had a hypothesis and then tested the hypothesis and then determined that it's a theory now, and we all use the theory of gravity. And then if I let go of the pin, it falls because of gravity, right? So laws and facts tell us what something is or what something does. Now, here's the thing. If I were to say, when I let go of the pen, it falls. If I add at De Anza College on planet Earth during these conditions, that would be a fact. If I let go of this 100 times out of 100, it's going to fall. However, what if somehow I won a trip aboard one of Jeff Bezos' rockets and I flew up into outer space and then I let go of the pen there? Would it still fall? No. The conditions have changed. And since the conditions have changed, it would float up there because it's much further away from the Earth. It doesn't experience the strong gravitational pull of the Earth because it's farther from it. In that case, it floats. So what happens there is I have what's called a law. So if I say just straight up, if I let go of a pen, it falls, that may be true in 99 times out of 100. If I go anywhere on planet Earth and let go of the pen, it's going to fall. But if I board a rocket and fly up to outer space and then let go of it, it might not. It might float. So a law is a generalization. It says what happens most of the time. It says what happens most of the time. But there can be exceptions. For example, there are these laws that we'll talk about when we get into talking about wind. These laws are called Newton's laws of motion. There are three of them. We're not going to get into them right now, but those three laws of motion actually have a very specific set of conditions that they need to occur under. If they do not occur under that very specific set of definitions, or that very specific set of conditions, then they break. Laws can be broken, just like you can break the speed limit. The speed limit 65, you're driving 80 on the freeway. You've broken the speed limit law. Well, laws can be broken. Isaac or Newton's laws of motion actually break down when the motion is either really tiny, or it's traveling really fast. And I mean like speed of light fast. In those conditions, Newton's laws of motions don't apply. So Newton's laws of motions apply in most scenarios, but there are some where it doesn't. So laws can be broken in certain situations. This is different from facts. A fact is an indisputable and objective observation of the world around us. On a perfectly clear sunny day, the sky is blue. Now, you may call it something else. That doesn't actually change the color of the sky. That changes what you call it. I may call it blue. You may call it azul. I may call it blue. You may call it green. That doesn't actually change what it is. In this case, it is indisputable and objective. So a law tells us what happens most of the time. A fact tells us absolutely 100% this is what happens. For example, I'm trying to knock off the De Anza College references, but I'm going to say one. This is De Anza College, where I teach at. If you're taking this from another school, I apologize. But De Anza College, today's date is June 24th, 2024. That just tells you when I recorded this video. June 24th, 2024. It is currently 6:01 p.m. where I'm located. Those are indisputable facts. Now, you may be in another part of the world where it's 9:01 p.m., or maybe it's tomorrow, June 25th, but the fact stays the same that this moment exists. And it is this moment right now. So, laws tell us what happens most of the time, how something behaves most of the time. Facts are indisputable, absolutely 100%. This is what's going on. The sky is blue. We are on planet Earth. Again, you can call it something else that doesn't actually change what it is. Has anybody ever told you, or have you ever heard of a story in the news of somebody saying something like, it's cold outside. How can global warming be real? There's actually a story one time of a senator, I forget his name. You could probably guess what political party he was a part of. Who walked outside the Senate chambers, grabbed a snowball, walked back in, and held it in front of everybody and said, how can global warming be true? And a lot of people buy that. My hope is that after this next part, you will be able to understand why that is not true. So what I want to do for just a few minutes is explain to you what good science is and then what pseudoscience is. Good science, scientifically valid conclusions, are going to have these qualities to them. The first one is they are based on substantial amounts of data. The bare minimum is 30. That is what's called the central limit theorem of statistics. And it basically states that you have to have a minimum of 30 pieces of data before you can assume that that data will have a normal distribution. And once it has a normal distribution, you can do all kinds of cool statistics to it. So we need lots of data. Now, typically, the more the merrier. The more data you have, the more solid your conclusion is going to be. A scientific conclusion is also valid if it implies in multiple situations or is universal. What this means is that You can't just say in this specific situation, like so global or it's cold in Long Beach, California on April 11th, 1983, and so global warming is fake. You can't say that. That is not a scientific conclusion. Why? Because let's say you go to New York, New York on the same day, and let's say they're experiencing record warmth. Somebody else can make the same conclusion on the other end and say, well, it's hot as hell here, so global warming is real. That's not true either. No, a scientific conclusion has to be based on, it has to apply in many different situations. It can't only work in one place. It would be like me saying all horses are black. All somebody needs to do is come and show me a pink horse, and guess what? Suddenly my conclusion is done. A scientific conclusion can and must be reproducible, meaning that other scientists need to do the same experiment and get similar results. And I would even say identical results. Now, there are, again, this is where statistics comes in. You would have to be able to prove statistically that the results you have are actually different. That's what's called statistical significance testing. So pretty much otherwise, if you can't prove statistical significance, then they're the same. So it has to be tested and reproduced by other scientists with identical results. And this is actually the peer review process. If you tell somebody how to do something and they do it and they get a completely different result, your scientific conclusion is not good. So there has to be a lot of data backing it up. It has to be applicable in multiple situations, and it has to be reproducible. Meaning others should be able to come to the same conclusion. Practically everything we discuss in this course or in any of my classes is valid scientific conclusions that have been tested by thousands of scientists and well accepted by meteorologists. Now, how does this differ from pseudoscience? Pseudoscience is something that is done all the time, where somebody will take one experience and they'll make a conclusion based off of that. So for example, maybe they'll say avocado is gross. And that's simply based on their experience of eating avocado. Somebody else eats avocado, they may love it. Pseudoscience is based on very little data, oftentimes just one data point. It's based on one specific situation. It cannot be applied in other situations. Conclusions are based on questionable, if not outright incorrect methods, meaning that the way that you came to the conclusion is not a scientifically acceptable way. You didn't collect the data properly. You didn't analyze it correctly. You didn't take averages. You didn't get enough data. You looked at one specific situation, and I'll give you an example of science and pseudoscience in a moment. And this is not to get political, but this is actually still very important. Let's talk about science really quickly. The Earth is warming up. This is a scientifically proven fact. This is reality. The average temperature of planet Earth has gone up significantly since the 1960s. And if you actually take a look at this long-term trend, you can even go back all the way back to there we go. Let me go back. I just gave you a spoiler alert to who I'm going to be talking about. But if you go back from here all the way to now, you see a very notable upward trend. From the early 1900s to now, there has been a very notable upward trend in average global temperatures. Now, that being said, where do we get these average global temperatures? Well, these average global temperatures are calculated from millions and millions and millions of pieces of data taken from tens of thousands of locations all over the world, filled in with satellite data for the areas that we don't have weather stations at, all using the exact same globally accepted methods of data conclusions, and averaged and reproduced by different scientists with practically the same results. Now, I will say there is some scientific disagreement. If somebody tells you that there is scientific disagreement, there absolutely is. Here's what scientific disagreement looks like, though. One agency may say that this is what's happening. Another scientific agency may say, well, oh, hello. Sorry about that. Another scientific agency may say, well, actually, this is what's happening. Maybe there was like a brief warming period that they didn't observe. What you notice is that both of them still identify the same trend. There is still an upward trend in global average temperatures. The only difference is exactly how much warming has occurred. But both of them are telling us the same thing. The Earth is warming. There's just maybe some disagreement on exactly how much. On the other hand, our former and future, hopefully not, president, I'll have to make a new video in 2025 to see if this is true or not, loves to use pseudoscience. These are two images from Donald Trump from Twitter back before it was taken over by Elon Musk, where he had cited different instances where on one particular day, during one particular time, and in one particular place, snowing in Texas and Louisiana, record-setting freezing temperatures throughout the country and beyond, global warming is an expensive hoax. Here's a funny thing. January 29th, 2014. I happened to be living on the West Coast during that time when he's talking about how cold it is on the East Coast. Guess what? On the West Coast, we were experiencing record heat. We had 90-degree days in January, like 80s in the Bay Area. That is outrageously warm. But he didn't mention that here. It ignored that. He only mentioned one instance, that particular day, and he only mentioned one location. He said, snowing in Texas and Louisiana, record-setting freezing temperatures throughout the country and beyond. He doesn't tell us where beyond is. He says throughout the country, but he only mentions the part that fits his narrative. That is pseudoscience. Making a conclusion saying that global warming is fake because it's cold in this one region, while completely ignoring the fact that it may be hot somewhere else. That is pseudoscience. He's making a global conclusion based off of one piece of data. And all you have to do is look at another instance to disprove it. This is like saying all horses are black and then showing him a green horse. Guess what? I just disproved you. That is pseudoscience, making a global conclusion based off of one instance. That is pseudoscience. So just a review before we continue on, a nice little road check for you. Science is the study of the world around us through observations and experiments. Observations involve just collecting data without doing anything. Experiments involve manipulating the environment and then observing the outcome. The scientific method is flexible and complicated. Theories are tested and proven, while hypotheses are only based off of prior knowledge. Laws are generalizations. Facts are indisputable. Science is based on many observations reproduced by many people using scientifically acceptable data collection methods, while pseudoscience does not. So that's an overview of science. Next, we're going to talk about the difference between weather and climate.